So far, we've talked about measures of variation or spread based on the range and the interquartile range. One problem with both of these measures of variation is that you're not including information from all the data points, from all the sets of observations. You're just looking at either the two endpoints in terms of for the range, or you're just looking at the third quartile and the first quartile for the interquartile range. We want a measure of variation of our data set that really includes all the information in our set of observations. One measure of variation that we might consider is to think about the average of the distances from the mean for our set of observations. To put it another way, we might view the variability of our data points in terms of the distance of each observation from the mean. For example, we could add up all the distances of our observations from the mean and then divide by the sample size. So this is also can be considered kind of looking at deviations from the mean. So let's look at a few examples. But the notation is really all you're doing here is for this sort of average of distances from the mean, you're taking each observation, subtracting out the mean, so you get the distance from the mean, and you're adding up all those distances or deviations, and then you're dividing by the total sample size. So let's look at a few calculations. Suppose we have a set of observations that just consists of the numbers 1, 2, 3, 4, and 5, so that sample size is 5. We know that the mean is simply adding up all those values, dividing by the sample size, so it's 15 divided by 5, or 3. So x bar, or the mean, is 3. That's the sort of typical observation in this set of observations. But suppose we want to look at this measure of variation in terms of distances from the mean. What we'll do is we'll subtract the mean from each observation and then calculate the average of those distances from the mean. So for example, for that first observation of I equals 1, the distance from the mean is 1 minus 3, or negative 2. But to really think about this in sort of visual terms, we can think about these observations of distances in terms of values above and below the mean. So here we have a number line. That middle part of the number line is x bar. That's the mean of our set of observations. And then we can consider our data points as lying above the mean and below the mean. So if an observation is higher than the mean, it's going to be in the positive range. If an observation is lower than the mean, then it's going to be in the negative range. So all of our observations, each observation can be thought of as how far is it from the typical observation in our data set as calculated based on the mean. So distances below the mean are in the negative territory. Distances above the mean are in the positive territory. And then if an observation happens to have the same value as the mean, it's just going to lie right on that middle part labeled x bar. So let's, for a reference, kind of extend the line for the mean just as a reference line. And we're going to look at the distances above and below the mean for our set of observations. So that first observation is negative 2 in terms of the distance from the mean. So the observation is 1. You subtract out the mean, which is 3. And so that observation of 1, it lies 2 values lower than the mean. So we might plot it as a line here. So that is that first distance from the mean. It's 2 distances, 2 units away from the mean. And it's lower than the mean, so it's in the negative territory. Our next observation is 2. So how far is it from the mean? Well, it's 1 value lower than the mean, so it's in that negative territory. You do 2 minus 3, and you get a value of negative 1. The next observation in our set of observations is 3. So how far is it from the mean? Well, you take 3 minus 3, and you get a value of 0. So that next observation lies directly in line with the mean. There's no distance from it from the mean. The next observation has a value of 4. So it is 1 unit higher than the mean. So we assign it a value, a distance of +1, because you take 4 minus 3, the sample mean, and you get a value of 1. And then finally, our last observation is a value of 5. So you take 5 minus the sample mean of 3, and you get a value of plus 2. So that last observation is now 2 units higher than the mean. So you can think of these 5 observations. All we've done is we've said how far are each of these observations from the sample mean. Some observations are lower than the sample mean, so they have a negative distance. Some observations are higher than the mean, so they have a positive distance. And one observation happens to have the same value as the sample mean, so it has no distance. It has a 0 distance from the sample mean. All we're doing is we're thinking of our data set in terms of how different each observation is from the mean. Right? We're just converting into these distances. Now, in terms of a measure of variability or spread, we might want to say instead of these 5 distances from the mean, we just want an average distance from the mean. Typically, how far off is an observation from the mean of our set of observations? Well, one way to do that is just to take the average of these distances. The problem is when you take the average of these distances, you get a value of 0. So as a measure of variation or spread in a set of data, a value of 0 is pretty meaningless. And as you can see, that there is some variation. It doesn't make sense to say that there's no variation because some points are higher, some points are lower, and there's one point that's right on the sample mean. But there is some variation in the data set, and this simple average of the distances from the mean, it's not reflecting the variation in the data set. And here's a problem. If you take the average of distances from the mean as we've calculated it, it will always equal 0. So if you just take the average of deviations or distances from the mean as a measure of variability, it doesn't work. You get a value of 0 each time. The basic problem is that the values below the mean cancel out the values above the mean. And then the value at the mean is simply 0. So the point is that you have these distances canceling each other out. And that's because the negative distances cancel out the positive distances. So what we want to do is we want to measure a variation that turns these negative distances into positive distances so we can add all of them up together and get a positive value for a, or at least a non-negative value for a measure of variability in our data set. So one way to think about it is that we can square these distances from the mean. So if you square a distance, meaning if you take it to the power of 2, then a negative number can be positive. So -1 to the second power is -1 times -1, which is +1. So squaring some value, some number, will turn that negative value into a positive value. And we like this because we can turn those negative deviations or distances, those values that lie below the mean, we can make them positive. So when we add up all these values and take the average, we can get a non-zero number. We can get a positive number. And so that's why we like to square these deviations or distances. It's so that we have a measure of variability that makes sense, that doesn't always add up to 0. That measure is called the variance. When we take these deviations, we square them and we add them up together and we calculate the average, that is the variance. Let's go through this example again. So that first deviation is -2. So that first observation of 1, it lies 2 units below the sample mean. Well, what happens when we square that value? Well, that's equivalent to making a box, because -2 times -2, or -2 to the second power, that is 4. So that area of the box is 4. Right? All we're doing is we're taking that deviation, that distance from the mean, and we're squaring it. That's conceptually the same as making a box. So rather than a deviation below the sample mean, we're making a box. We're just squaring that deviation, and now that sort of distance from the sample mean, that distance is now represented by 4. Okay, so we're looking at that area of that box, which is 4. Let's take our next deviation. It's -1. So that next observation, it is a value of 2, and 2 is, in fact, 1 value below the sample mean. Well, if we square it, we take -1 to the second power, which is -1 times -1, and so that box has an area of 1. So instead of assigning that second observation a distance of -1, we now assign it this distance, this square distance of 1. that next observation has a value of 3, and since the sample mean is 3, that distance is 0. Well, if you take the 0 times 0, or 0 to the second power, you get a value of 0. So that distance for that third observation is still 0. If you look at the next observation, we have a value that is greater than the sample mean. So the next observation has a value of 4, so its distance is actually 1 unit higher above the sample mean. Well, if we take 1 to the second power, 1 times 1, we get an area of 1. So the squared distance of that observation from the sample mean is now 1. So instead of positive 1, it still gets a value of positive 1, but it's really 1 to the second power. That final observation has a value of 5, so you take 5 minus 3 and you get a value of 2. That it really means that it's 2 units above the sample mean. Well, what happens when we take the square of that distance? Well, you take 2 to the second power and you get a value of 4. So that squared distance, instead of being 2, it's now 4. All we've done is we've taken these distances from the mean and we've turned the negative values positive by squaring them, and we've taken the positive values and just inflated them by squaring them. You can see that instead of just looking at the distances, we're now looking at the squared distances from the mean. And all the values are either positive, or if it's just right on the mean, that for that particular observation, it now has a value of 0. The nice property of these distances is that we can now calculate an average of these squared distances, and that average of squared distances will be positive. So conceptually, you can think of the total variability in this set of observations. It's just simply the sum of these areas of these boxes. So 4 plus 1 plus 0 plus 1 plus 4. You're adding up the area of these boxes. That's sort of a snapshot measure of how much variation there really is in this set of data. And so when you add that up, you get this value of 10. You can see that there's quite a bit of variation. But the variance for this set of observations, we want to think about the average of the variability. But before we do that, I want you to think about in terms of what might constitute less variability and what might constitute more variability in a set of observations. So a set of observations with less variability, you have data points that really aren't that different, you're going to have a smaller total area taken up by these boxes, meaning the sum of the squared deviations or distances from the mean, it's going to be smaller. So in this case, the sum of the squared deviations from the mean is 1 plus 1 plus 0 plus 1 plus 1. So it's 4. And you can visually see this. The area of the boxes, it's just smaller. You add up the total area. A set of observations with greater variability, it's going to take up more area if you just look at the area of the boxes. So in this set of observations, it's a different set of observations, you have more variability. You can see this. To put it another way, the sum of the squared distances from the mean is higher. So you add up the area of the boxes. So you can see that this sort of squaring of the distances from the mean, what happens is that it still encompasses the variation of the data set. So if you have a data set with more variation, the sum of the squared distances is going to be greater. If you have less variation in your data set, the sum of the squared distances or deviations is going to be smaller. But we want to look at sort of a single number in terms of the variation. And that single number is the variance. And the variance is the sum of the squared distances from the mean divided by the sample size. So let's look at this again. For our original data set, in which we had values of 1, 2, 3, 4, and 5, if we take the average of the sum of the squared distances from the mean, we get a value of 2. All we're doing is we're adding up the areas of these boxes, and then we're dividing by the total number of boxes, or the total number of observations. So 10 divided by 5 is 2. 10 here is the total variability in our data set. 5 is the number of observations. So as a number of overall variation, we get this value of 2. That value is known as the variance. When you take the sum of the squared deviations and divide by the total number of observations, you get the variance. The units for variance, because the distances are now squared, the units of the variance are in terms of units squared. So in this data set, suppose our units were miles. Well, then the variance would be expressed in miles squared. if our original data set consisted of units of inches, the variance would be expressed in inches squared. And that simply reflects the fact that we're calculating the variance based on the square deviations from the mean. Right. Now, one way to kind of think about the variance is that it's really a typical box in our set of boxes. So each observation we've translated into a box because we're just taking the distance and squaring it. But the variance is kind of like, okay, well, what's the typical box? What's the sort of typical squared deviation from the mean? So for our original data set, when we had values of 1, 2, 3, 4, and 5, the typical box has an area of 2. And we've shown it here to give you an idea of what the typical box looks like. This represents sort of a typical square deviation from the mean. And you can see that this box, it's not the biggest box, it's not the smallest box, but it's kind of gives you an idea of how varied the set of observations are in our data set. Now, the important point is that the variance reflects the variability in our data set. So a data set with less variability, it's going to have a smaller typical box. It's going to have a smaller variance. A data set with more variability, it's going to have a larger typical box, reflecting the larger degree of spread or variation in the data set. So if we look at this data set, which has a smaller set of total variability, the total area of the boxes is smaller. The typical box for this set of observations has an area of 0.8. To put it another way, the variance is smaller when the total variability is smaller. So for this example, the total variation, the total sum of the squared deviations around the mean is 1 plus 1 plus 0 plus 1 plus 1 divided by 5, or 4 divided by 5 is 0.8. So that's the variance for the set of observations. The variance for a data set with more variability has a box that is a little bit larger. So for this case, the variance is 9.4. The area of a typical box for this set of observations is 9.4. It's calculated the same way as before. You take the total variability for a set of observations, and then you divide by the number of observations. And we get this value of 9.4. So you can see that the variance as the average of the sum of the squared deviations around the mean, the variance does reflect more or less variability in a data set. A higher value of the variance suggests greater variability in a set of observations. A lower value of variance suggests a lower level of variance. But one problem with the variance is that it's expressed in units squared. And typically we want to think about a measure of variability in terms of the underlying units. So if our set of observations is expressed in miles squared, you want to think about a measure of variability expressed in miles, not just miles squared. So this highlights one problem or disadvantage with the variance, which is that it can be difficult to interpret. When a measure of variability is in terms of units squared, what does that really mean? So one solution is to really think about a measure of variability that is based on the underlying units. So instead of units squared, it's in terms of the units. Instead of inches squared, it's based on inches. Instead of miles squared, it'll be based on miles. A simple solution is just to take the square root of the variance. The variance is based on squaring the deviations or distances from the mean. So to kind of undo that squaring, we just take the square root of the variance. When we take the square root of the variance, we create a measure of variation called the standard deviation. So the standard deviation is just the square root of the variance. So let's look at our set of observations for a data set of 1, 2, 3, 4, and 5. And let's think about what the standard deviation means. The variance is, as I mentioned earlier, is kind of like the typical size of the box for these set of observations. It's the typical square deviation from the mean. To calculate the standard deviation, you just take the square root of the variance. So for our set of observations, the variance is 2. The square root of the variance is 1.41 roughly. The great thing is this value for the standard deviation, it's now back to our original units. So if our data set is in miles squared, if our data set is in terms of miles, the variance will be in miles squared, but the standard deviation will be in miles now. So that's one great thing about the standard deviation. But what does the standard deviation really mean? Well, you can think of the variance as the typical square deviation from the mean. The standard deviation is really the side length of a typical box in our set of observations. So the variance is 2, the standard deviation is 1.41. So the standard deviation is really just the length of one of our boxes. It's the side length. And if you take 1.41 to the second power, you will roughly get a value of 2. And that just reflects the fact that the square root of the variance equals the standard deviation. And if you take the square of the standard deviation, you get the variance. So in many ways, the variance and the standard deviation are quite equivalent. But we like the standard deviation because it's based on the underlying units and not the unit squared, in contrast to the variance. So if we look at a data set with smaller variability, the variance will have a lower value. So, and in the similar way, the standard deviation will also have a lower value. So for this data set in which we have a sort of smaller degree of variability, the variance is 0.8, and then the square root of that variance is 0.9. To put it another way, the side length of our typical box is 0.9. So the standard deviation of 0.9 is reflecting the smaller degree of variability in this set of observations. If we look at a set of observations with greater variability, right, the variance is going to be larger. So the typical box, the typical square deviation from the mean is 9.4. And if we take the square root of that, we get the side length of our typical box, which is roughly 3. And so that is the standard deviation. The standard deviation is simply the square root of the variance. And this standard deviation is larger. Instead of a value below 1, we now have a value above 3. So this greater degree of variability in our data set is reflected by a larger standard deviation. So you can see that the total variability, the variance, and the standard deviation, they all change depending on the spread in our data set as calculated based on the deviations or distances from the mean. So let's return to our original data sets. And we have these values of 1, 2, 3, and 4, and 5. And we have these distances above and below the mean. These are just the distances, and they aren't squared. But the standard deviation is the side length of our typical box. It's the side length of the typical square deviation from the mean. Now, when we look at the standard deviation for our data set, we get this value of 1.41 units. That length is given here. Now, if we compare that standard deviation to the actual deviations or distances in our data set, you can see that it's pretty similar to these distances or deviations, but it's not the smallest, it's not the largest. It's kind of a typical distance from the mean. So the standard deviation can be viewed as a typical distance from the mean. For a set of observations, how far off, on average, is an observation from the mean? And if we sort our distances from the mean, you can see the standard deviation, it looks pretty typical. Right? It's not the smallest distance, it's not the largest distance, but on average, if we convert our distances into sort of a positive value, the standard deviation will be the typical distance from the mean. To put another way, the standard deviation, it is a standard deviation. So one great thing about statistics is that the language tries to be pretty clear. We try to be pretty clear about what we mean. So when people say, what is a standard deviation? You can say, well, it's a standard deviation. It's a typical distance or deviation from the mean. And what's useful about the standard deviation is that the greater the standard deviation, the greater the variability of a set of observations around the mean. And the standard deviation, as well as the variance, they both include information from all the observations. Unlike the range or the interquartile range, you're calculating the standard deviation variance based on all the observations. The other great thing about the standard deviation is it converts all this information about these observations into a single number. So we have a single number summary for the amount of variability or dispersion in a set of observations. The greater the value of the variance or standard deviation, the greater the variability or spread or dispersion of a set of observations around the mean.